let's move on to our next speaker, who will be introduced by Steve Dotson, also known as Stargazer Steve. Our next speaker is Alan Ward. He'll talk to us about optical coatings and oilings for astronomical instruments. So go ahead, Steve.
I'm speaking from Alan Ward's vacuum coating room in his backyard shop in Sudbury, Ontario. And I have known and worked with Alan ever since he started his prolific telescope making career about 40 years ago. Several years before that, as a teen, he had become fascinated with the possibility of making your own telescope when he read an article about it in the Popular Science Encyclopedia. But one sentence that you can see in the yellow stopped him cold. You have to send your work away for the shiny aluminum coating. Fortunately, that dream of telescopes came back into focus when he met Sudbury's telescope pioneer, Ken Odaisky. Ken had made a gaggle of scopes, many with mirrors he had silvered himself. With Ken's example, Alan quickly gained experience and became a telescope mentor to many at Science North. Of course, Alan soon realized you could skip the send away part of the mirror making by making a lens instead. So Alan's next telescope was a refractor. Now he makes world-class apochromatic refractors that have won many prizes at the world-famous Stellafane convention. But Alan was far from done with mirrors. The next bold step was to renovate several mirror coating plants and become an expert in their use. And some of you may have seen Alan at Starfest in 2003 when he successfully illuminized a telescope mirror in the field with his portable coating plant. More recently, he transported that equipment 1,000 kilometers to Stellafane in Vermont to provide the first ever illuminizing service there, coating 15 mirrors as a convention volunteer. Some of the people will recognize the man on the right is Al Nagler of Eyepiece fame. Few people know the theory and practice of what goes into and on astronomical optics like Alan. So I'll turn it over to him now.
Well, thank you very much for that, Steve. And I can't believe that 40 years has already gone by. And wow. And another thing too, this year actually marks at this meeting, this marks my 25th anniversary for actually giving this talk. So I started giving these talks on coatings back, my first one was done at the University Star Party in 1996. So we're running short on time. So I'm going to go through this pretty quickly. And I'm sure you're all going to find this topic quite fascinating. You all know the David Dunlap Observatory. This is when during the 80s, when I knew Ken, we used to basically wrap up a bunch of mirrors from up north here and make the pilgrimage down south to Richmond Hill to have our mirrors coated. And I made this rack so that the DDO can multiply coat several mirrors at once. So that was quite handy. I believe that rack is still being used today. So two parts to my talk. I'm going to explain to you how thin film coatings work, and also we're going to go over how they're applied to your optics and telescopes. So as you know, thin films can be used for a variety of things for astronomy. We use them for reducing unwanted reflections from surfaces of lenses, like eyepieces, or lenses for telescopes. We use them also to enhance the reflectivity of mirrors. You've heard of enhanced coatings. And we also use thin films for making optical filters, like O3 filters, dark sky, deep sky filters, that sort of thing. And they all use pretty much the same kind of process that I'll be explaining about. And they all work based on the same theories. But I need to digress a little bit in order to explain how these coatings work. And in order to do that, I need to kind of explain a little bit about how light works. And the best way to do that is to use wave theory by using water as an analogy instead. So as kids, we used to, throw pebbles in the pond, and we see the wave pattern basically all travel out in all directions in straight lines. And but if you ever look closely at these ripples of water, it's actually the water is actually stayed put. It's the energy that has traveled from one spot to the other. So if you drop a pebble in a pond in a pool, for example, you'll see the wave travel from left to right. It's actually the water is not moving. It's the wave and the energy that's moving. And and you can see sometimes you put like a toy boat or something like that in the pool, it'll actually just kind of like it'll go basically go up and down sort of thing. So just keep in mind that the water is actually stayed about where it is. It's the energy that has moved. We've all heard of tsunami waves. They can travel as fast as a jetliner, believe it or not, up to 500 miles per hour. But as they get closer to the shore, they slow down and grow in height, and that's where the damage is caused. Now, marine architecture has actually used the theory of thin film coatings in order to reduce waves. And as you know, in an ocean liner, we have this huge bow wave that causes tremendous drag on a ship. And if we can somehow, and these waves, like this bow wave can be seen for hundreds of miles, and it produces tremendous drag. So we need to somehow reduce or eliminate this wave. So how can this be done? Well, this is done by introducing a second wave. And this is done by introducing a protrusion that you can see in dry docks. It's called a bulbous bow. And in dry docks, you can see this onion-looking thing sticking out in the front, but it's normally underwater. So that's why you only see it in dry dock. But what this bulbous bow does is as the ship is traveling in the water, it actually creates another second wave, but this wave is slightly different. It's not as big, however, it's only maybe about 15% as big as the initial bow wave. But as you see by the diagram, then it's out of phase. So these two waves basically add together and they subtract, resulting in a slightly less resultant wave that's only 85%. So basically, we can save almost 15% energy in fuel by doing this. I'll skip the skipping rope analogy. So congratulations, you now earned your degree in wave theoretical physics. Now let's observe what happens to light waves when they strike glass surfaces and other materials, such as glass. So uncoated lenses, we know that when you look at an uncoated lens, you see a lot of glare, a lot of that's because the light is being reflected from the glass on both sides of the lens. And if you have multiple lenses, it gets even worse, right? So this reduces the brightness at the final image. It also loses contrast. And the stray light is very, very unwanted. So we need to find a way of reducing these glares and increasing the light transmission through the lens. How do we do this? Well, you'll see. Let's first show exactly what happens when light enters a single piece of glass. Here we have light coming in through the air and it strikes a glass surface. And of course, we see a reflection. And reflection is approximately about 4% on bare glass. And the rest of the light goes through. We're not going to take into account any absorption. We'll call it zero. And of course, we get the same reflection happening at the back end of the glass as it emits through. So by and large, we get basically a very low percentage of light going through the lens. That's uncoated, around 92% or so. Not very good. And you can just imagine how worse it gets if you put multiple lenses in there that are not coated. So how can we reduce these reflections? Well, what we do is we add a second wave, just like the bulbous bow did, and we use thin film coatings to do this. So one of the materials that's commonly used for lenses is magnesium fluoride. It has, as you can see, it has a slightly lower refractive index than glass does, and that's important because whenever light strikes an index of refraction that's lower than glass, we create a smaller reflection. So as you can see here, the first reflection off the magnesium fluoride boundary is only about 2.5% compared to bare glass, which was 4%. The rest of the light goes through unabsorbed. But then again, the magnesium fluoride, the light going through the magnesium fluoride boundary now enters into glass, which is a higher index of refraction. So we get another reflection going on here. But as you can see, the light is traveling into the magnesium fluoride a quarter wave thick, and it's exiting out of the magnesium fluoride by another quarter wave. So now it's a half a wave out of phase. And so we have two reflections that are out of phase with each other, similar to the bulbous bow. When you add them together, you get a resultant reflection that's only 1.4%. So we went from 4% from bare glass to now 1.4% reflectivity by just introducing a simple thin film coating, such as magnesium fluoride. The same thing happens on the back side of the glass. We had the same coatings there, and of course we get a much better improvement in light transmissivity. Now, this doesn't work perfectly. In order to cancel out the light perfectly, all of these conditions have to be met, and of course they never are, because we can only have a quarter wavelength of a material for a certain color of light. So we basically optimize it for the middle of the spectrum around green or yellow, but then the reds and the blues, they're going to reflect more than the greens will. So how do we improve that? Well, that gets a little bit more complicated. I won't get into it, but that's what multiple coatings are used for. But here's the effect that you would see. When you coat a lens, let's say just in the center part, we create the optical hole effect. And normally when I give this talk live, I pass around this lens, and you can actually, no matter how you look at it through the light, you can't see no glass there. The only way to tell it's glass there is by touching it. Then you get fingerprints on it, and then everybody gets upset. So, but anyway, this is the effect that happens. The coating is very, very thin. It's about 100 nanometers in physical thickness, very, very thin. But that's all else required to get this optical hole effect. And here's another piece of, this is a picture window glass that picture frame glass that I used as a demonstration as well. As you can see, the glare off the uncoated section is quite prevalent, but the center part is coated. Now this is just with a single lens and reflective coating of magnesium fluoride. So multiple coatings involve many, many layers. Like if we wear eyeglasses or lenses for cameras, they can have 5 to even more different coatings on them, and they tend to straddle the spectrum to make the glass even thinner, almost invisible. Now let's go look at how mirrors are done with thin films. So typically an aluminum coating is very, very thin. It's about 600 atoms thick, or 60 nanometers in this case. And the problem with aluminum is that in a vacuum, it reflects 90%, but as soon as you introduce it to air, it immediately oxidizes, and you get a 10 millimeter aluminum oxide that forms on it. And this now reflects the light. We only get an 87% reflection off the aluminum. Not very good, especially if you have 2 or 3 reflections in your telescope. You would be down to 65% with 3 reflections. So not very good. So we need to improve the reflectivity of the aluminum. Now, we used to use silver in the old days. Silver was 98, 99%, but the problem with silver is that it tarnishes. It reacts to the sulfur, and it causes sulfur sulfide to form, which is that ugly yellow appearance that you would see over the course of a year, especially if you lived in Sudbury. So enhanced aluminum coatings, you've heard the term. And all we're doing here is we're doing something similar to what we do with the lens. We're adding dielectric materials, but instead we're adding these dielectric materials onto the aluminum. You can also use, you've heard of dielectric mirrors such as star diagonals, where there's no metallic base. There's typically about 40 layers of coatings or so, and they're all done by using dielectrics materials. And these are all transparent materials, and by adding them certain ways, you can actually create a mirror that's almost 99.9 reflectivity. The problem with these types of mirrors is that they're disposable. They cannot be stripped. But enhanced mirror coatings can be stripped, and that's the beauty about them. And they can give you a lot more reflectivity as well compared to bare aluminum. And this is how we do it. So instead, we use magnesium fluoride as well and cerium dioxide, but we do the coatings oppositely that you would do in a lens. So here we're creating. Let's go through what goes on. So light's coming in, and it hits the cerium dioxide boundary first, which is very, very thin, quarter wave thick. And it's got a very high index, 2.3, which is a very high index of refraction. So we're going to get a huge reflection right off the bat, 34% for the cerium oxide boundary. So the rest of the light goes through, and it hits the magnesium fluoride boundary, and we get another reflection. This reflection is about 13.5%. And then finally the light finally hits the aluminum boundary, but by that point, we've already reflected almost 47, close to 45% of the light already by the dielectric. So the aluminum coating is going to reflect basically it's going to reflect whatever else is hitting it, and it's going to take a 5% loss. So basically we have 3 reflections that are adding in phase, as you can see here, resulting in a overall reflectivity up to 95%, which is pretty good. the whole thing with the aluminum coating is that it wants 10% of energy, whatever hits it. So in this case, it's only absorbing 5% because 50% of the light or so has already been reflected by the dielectric coatings. Now this is just a very simple, you can increase this again by adding another pair of cerium dioxide and magnesium fluoride, and that way you can get up to 99% as well. But it gets pretty tricky when you do that. And it's very, very hard to do these types of coatings on large surfaces as well. So here's a chart just giving you an idea as to the efficiencies of the different types of coatings and how many reflections you're dealing with. So as you can see in a cast grain, let's say we had 3 different reflections or so, you'd be down to 66% efficiency with bare aluminum. But with enhanced aluminum, we're up to 86%, which is a 20% improvement. And then if you had silver or a dielectric mirror, for example, you'd be up to 94%. So it gets pretty good. That's why it's a necessity that mirrors get enhanced aluminum. Some of you have high-end refractors such as the apochromatics that use oils as well as coatings or a combination of the two. And this is how the Oilings works. So for my apochromatic refractor, it's an oil space triplet. There's no airspace, but there's 3 different lenses. And what's nice about these Oilings is that they eliminate a lot of problems. First of all, they eliminate all the internal lens reflections. They eliminate any irregularities, so the internal surfaces don't need to be figured. They just need to be more or less polished. It's not affected by temperatures, and these can be maintained clean indefinitely. Now, what the thing is, the oil is pretty expensive. It's about $150 an ounce, but you don't need very much of it to do the task. So basically, the lenses look like this. There's 3 different types of glass. As you can see, they have different types of indexes of refraction. But what we want to do is choose an oil that's in between the adjacent lenses. Okay, so so they best match. So we want this glass to disappear when we put this oil in. And that's what's nice about these oils. You can get them made to any refractive index you want, and that's why they charge the big bucks for them. But so this is how it works. So you can actually get away with just oiling these lenses and not have to do any coatings on them whatsoever. So I'll get Andrew to show you the disappearing Beaker video, and this basically exactly simulates what happens in an oil space lens when you use the oils instead of coatings. So Andrew, you're showing the video right now? Okay. Yeah, so the oil is basically filling in the small beaker within the bigger beaker. And as you can see, as it fills up and it displaces the air, the internal beaker basically more or less disappears, as you can see. Now, normally I do this with a live bed demonstration where I pass it around so everybody can see. Okay, so that's pretty much the effect, what you're seeing here. Okay, now we'll go on. All right, so that's basically how the coatings work. Now we're going to show you how they're actually put on the optical surfaces. So here's my shop here in Sudbury. Enter at your own risk. Here's a picture of the Bay Area, the lab where we do the log grinding and polishing of the optics. There's the polishing machine there, up to a 30-inch or so. I'm a collector of hot sauces as well. The coating room's in the back. We have an optical testing tunnel that's all computerized. And inside the coating room, we have got a dual bell jar system. One of them is strictly for doing dielectrics and silvering, and the other chamber is used for enhanced aluminum coating. So this is a vacuum. Most of the technology that you see here has to do with creating a vacuum. So there's a lot of pumps and also electrodes and that. And the optics, or what they call the substrates, or it could be a mirror or a lens, they're suspended upside down, as you can see here, facing down so that no dirt falls on them. And we have the vapor sources are located down below. And we got a closer look at them here. And so this is just an example of an aluminum vapor source and a silicon monoxide vapor source. We call these filaments or vapor boats. Some of the terminologies that we use here. So we use a tungsten filament for evaporating aluminum, and it basically looks like the same kind of filament that would be in an incandescent light bulb. And what we do is we hang off pure aluminum crimps, about eight of these or so, 80 to 75 milligrams each. Everything's pre-weighed, so we get exactly the same coating thickness all the time. So a lot of current goes through this filament, about 400 amps. And what happens, the aluminum will melt at 600 degrees Celsius, and then it'll start getting hotter and hotter and hotter. And at about 1200 degrees Celsius, it'll actually boil off because it's in a vacuum. So it'll turn into a vapor, and the vapor will go in all different directions. And a very, very thin coating will actually deposit and condense on the glass substrate. No more than 600 atoms thick. Which is about 1,000 times thinner than saran wrap. So it's a very, very thin coating. You don't want to go too thick, otherwise the aluminum starts losing its luster and it'll look like a white piece of paper if the coatings are too thick. And if the coatings are too thin, then you can see light through them. So there's a happy balance there. Basically, we put a coating of 60 nanometers or so on there, and that makes it nicely opaque. Another example of some of the silicone monoxide boat. You can do silver. You can do silver in here as well. Silicon monoxide, sometimes used as a protective overcoat. I don't recommend it because silicon monoxide takes a long time for it to naturally oxidize in air, and it also reduces the reflectivity of aluminum even more so than 87%. So the enhanced coatings is the way to go. So here's the chambers when they're pumping down. So most of the work is in the taking the air out of the chamber. It's actually most of it's actually water vapor actually. Sometimes I like to get visitors. We've had the occasional celebrities. I would drop by once in a while, like Dave Lee and Thomas Bopp here back in '97, and they signed my machine, and we spent an evening with them. So the mirrors, like I said, are suspended upside down. Here's a 16-inch mirror that we're putting in here, and you got to be careful not to drop these things. And so we start the pump down. So during the pump down, we do what we call molecular sandblasting, which is like an ion plasma discharge, where we apply 15,000 volts to the residual atmosphere. What this does, it bombards the surface of the glass with ions, so that it basically rips off all of any water molecule, because a lot of water likes to stick to things. It's like if you ever take a propane torch to a piece of glass, you'll see the moisture dissipate from it, and then you remove the torch, and you'll see the water basically reform right back on the glass. We got to get rid of this water, otherwise the coatings won't stick very well to the substrate. So this plasma discharge is used for a good 20 minutes, and it basically rips off all those water molecules off the glass substrate, making it perfectly dry. Here's a process schematic of my little chamber, that portable coating machine. Basically, it uses the same process as my bigger machine. This portable unit needs cold water to run through it at all times in order to keep the diffusion pump hot at the bottom and very, very cold at the top. That's how the system works. So it's similar to this is the picture of a diffusion pump. And the way it works is similar to your shower head in your shower. When you turn the water on, the water sprays out of the nozzles. We can imagine having 7 layers stacked on top of each other of nozzle heads. And this oil is being boiled down below, and it's going up this chimney, and it's spraying out at supersonic speeds. And so the oil is actually pushing down on the air, pushing it out, not sucking it out. And so we need to get down to like a very, very high vacuum, millionths of an atmosphere, similar to where the space shuttle flies at. Otherwise, when we vaporize the aluminum or other coatings, they'll oxidize. in their travel to the substrate. So that's why we need to take out all the air as much as possible. So the pump down takes about 45 minutes to do. That's how long it takes. But the actual coating actually takes very, very little time. It only takes maybe a couple of seconds for the aluminum to vaporize. It's done in a split second. The other coatings, like magnesium fluoride and cerium dioxide, they may take up to several minutes to coat, and that's nice because you need to monitor the thickness as you're depositing those materials. So, in order to get the proper enhancement that you're looking for. So here's what's inside of a diffusion pump. These are the shower heads I was telling you about. This is when I was refurbishing this machine back in the early 90s. There's no moving parts to this pump, believe it or not. The oil basically boils at the bottom in a boiler, and the oil vaporizes and it rises up into this chimney, a stack of shower heads, and then there's little holes, as you can see there, and the vapor is so strong, so powerful that it sprays downwards, and then it gets cooled by those cooling coils that are around the pump. And the vapor now basically rains down, pushing the air out where it escapes out the side. There's another pipe just above the oil where it's boiled, and that's where the air is taken outside. So this is the mirror that's just being coated. Now, when you ever look at a mirror that's being coated, and if it has overcoatings on it, you'll see certain features on it. And these are interference colors that you will see. And so one of the things that we do, these coatings have to be baked at a very high temperature in order to be cured properly. So they're baked in air in an oven at about 250 degrees Celsius in order for the coatings to cure. And as they cure, you'll see you can see these interference colors, and you can only see these edge on, or kind of like at an oblique angle. When you look at a mirror face on, you should not see these colors. It should be perfectly white. But on the angle, you'll see certain colors. You might see magenta, yellow, and green. And depending on the type of coating that you have, it'll give you different distinguishing colors. So the color tells us how thick the coating is. That's how we know. That's how we can tell how thick the coating is. So when we're putting on the magnesium fluoride, okay, we'll see it go from a yellow to a magenta over a few minutes, and then we stop it around a magenta color, and then we introduce the cerium dioxide, and the cerium dioxide will then change the color from magenta to green, and then the green will slightly go away. And this is face on. So, but when you look at it on an angle, you'll see these interference colors. There's the oven. This oven's never seen food, by the way. It's only seen glass. And this was this is my portable coating machine, which we brought to Sudbury a couple years ago, and it's all. I made it all Bluetooth controlled. I brought it to 2003 at StarFast, but it was a pretty simplistic machine at that time. So I've improved a lot of electronics on it and plumbing lines and everything else. So, and then with the latest Wi-Fi and Bluetooth technology, I made the coating all basically all controlled through my iPhone or on my iPad, and it was kind of fun for the spectators to basically actually operate the machine. All you had to do was push some screen buttons on my iPad to turn it on, and it would do its thing. So this is the very first mirror that we coated at Sudbury, and this member got her first indoctrination into the Springfield Telescope Makers Club by making her mirror herself, and we have, for historical reasons, we had it coated right on site at Sudbury. So that was quite a remarkable time we had there. I coated up to almost 15 mirrors that day, or that weekend. And so it was a lot of fun. That's pretty much it. I'm almost, just about time out. So any questions for anybody?
Well, Alan, fantastic. Thank you so much. Fabulous information and very, very interesting. I think we're going to get a lot of questions, so I'll turn it over to Emma.
Okay, first question is, how often is the new coating applicable? What testing is done to know that a new coating is needed?
Yeah, this is a tough question. So when you look down a telescope, even a very dirty mirror will look almost not too bad. But what you do is you take a very bright light, like a big spotlight or a torchlight, what I call it, a really good light, and when you shine it down the mirror, it'll tell you that if it's say this doesn't look too good, it'll show its face very, very easily. The other best way to do it is to take the mirror right out of the telescope and look at it under a very bright light, like a fluorescent light. Look through the back of it. If it starts to get worn out, it'll start to thin out. So you'll start seeing the light through it. You'll see a lot of pinholes through it. What you don't want to do is make sure that there's obviously no exposed glass. That's a bad news, because if there's any exposed glass, that glass is now weathered. Okay, it's got attacked by dew. It's lost the atoms and the molecules that allow it to bond properly to the coatings. So the glass has to be always pure in all respect. In other words, like it almost has to be as pure as being taken right off the polishing lap and cleaned immediately and coated. Glass cannot be left to the environment, like rain and dew and all that kind of stuff, so it'll get damaged. So it's an unfortunate thing to go through. I've received many mirrors like that they've just gone turned into such bad shape that the only recourse is because what happens if you try to coat those mirrors, the coating will just flake right off. It's just like rust. You're trying to paint over rust on a car. You got to bring it down to a new surface again. That means sanding it. We don't do that with mirrors. We polish them and figure them, but it's the same idea. Typically, coatings should last you. Bare aluminum coatings have been known to last 3 to 5 years, but the enhanced coatings now are much durable. And the commercial mirrors now that you buy through telescopes, they're all enhanced, and they last many years. Many years. Enhanced coatings are very durable. During my talks, I have many samples that I send out to the audience, and I give them scouring pads. You know the scouring pads that you use, those green scouring pads that you use to clean your dishes with? I actually have people try to scrub off the coatings. They can't even make a mark on them. So they're quite durable physically, but still, I would treat them with great respect. Keep them out of the dew. Try to prevent them from getting wet or dew on them at all costs.
Thank you. Is there a way an amateur can measure? Is there any way amateur can measure the reflectivity efficiency of a mirror at home with basic equipment?
To get an actual quantitative result, it's kind of difficult. But here's what I do. As a qualitative result, what you do is you take a piece of a piece of white paper, and you put it beside your mirror under a very bright white fluorescent light. And then what you do is you take 1 ply of Kleenex or Kim wipe tissue, and you place the tissue on top of your mirror and on top of the white piece of paper. The tissue on the white piece of paper will tell you what a perfect mirror would look like. Okay, so what you're going to see on your mirror is as it degrades, it's not going to look white anymore. It's going to look very dark gray. And that's what happens when a mirror deteriorates. You can easily, so what you're doing with the tissue paper is what you're converting the specular reflectivity of the mirror to a diffuse reflectivity of the mirror. And what it does, it tells you how bad the coating is in terms of color now, because now the color is scattered. And so as the reflectivity drops, okay, the color is not going to be as white anymore. It's going to start going darker and darker. So if I've ever looked at the eye plays a lot of tricks on you. So if you ever looked at a chrome mirror, for example, or even a silver mirror, it's very odd, very eerie to look at, because actually a chrome mirror or a silver mirror, like a silver, does actually look kind of dull. Like it doesn't look, especially silver. You can put a silver mirror against an aluminum mirror. There's something odd about it, because the silver mirror looks kind of like, doesn't quite look right. That's because your eyes are playing tricks on you. you put the white piece of paper trick that does it, with the tissue. It tells you how really good the reflectivity is. So that's one way that an amateur can easily tell as to how good or bad the coating is. And another thing too, when you put the tissue paper over the coating, you'll actually see the interference colors as well. So if the coatings were put on too thick, in other words, the dielectric coatings were put on too thick, they'll stand out. They'll stand out quite a bit with doing that test. So you can actually do a lot of qualitative testing on your own without using any fancy equipment.
How long did it take you to learn this skill?
Yeah, that's the scary part. I had no. I was so naive when I acquired this machine. I totally rebuilt it, but it took me a year to get it working, and I had no idea what was involved. Like I ended up buying books on it, going online, learning from other people. It actually took me like almost a year. Like aluminum is pretty simple. Aluminum's pretty, straightforward. It's kind of like whatever. But the overcoatings were quite complicated to learn how to do, and you just tear your hair out learning how to do it. But once you learn, it all makes sense. Just like everything else, I guess. But I found it's a fascinating science. It really is. It's almost like magic, that you're able to do this kind of stuff. With vacuum, vacuum science is quite it's a very interesting science to delve in, and it's very entertaining too to watch. I wish more people would come up to visit me and actually see the progress, actually see the actual procedure. It's quite something to watch, actually. Yeah.
For oil-spaced groups, what about the glass surfaces on the exterior of the lens, where the light beam enters and exits? Are they coated normally?
Yeah, for commercial lenses, of course, they're coated as well. So that gives you just an overall better transmissivity, of course. We did a test with my lenses against a lens that was coated with magnesium fluoride, all 6 surfaces. We had it tested at a professional lab where they were able to do a full spectrum analysis for all colors. And it was very interesting to watch because my oil-spaced coatings turned out better, had more transmissivity to them, even though my R1 and the R6 surfaces were bare glass. It had more transmissivity than the air-spaced coatings that had magnesium fluoride on all 6 surfaces. So it's very inconsequential to see the difference. I would assume that for photography purposes, for sure, you would want the front and the back lens sides to be coated. But I'm more of a visual observer myself. I don't do photography, but I find this inconsequential. And also, coated lenses, as you know, are very, very hard to keep clean. Just like I've worn glasses all my life, and it's just every 10 minutes they're dirty all the time. So it's like what's nice about bare glass is that they're very easy to keep clean, and they can be clean right out in the field very easily. So I'm not losing much light. I'm getting still like over 93% throughput, even with my oil-spaced lenses.
Now, are the coatings different for different scopes?
True, they are. Yeah, there's different formulas. You can design the coating for whatever you want. So, like, let's say your hydrogen alpha light or whatever. So, what you like typically for visual purposes, we choose the coatings are basically designed for the middle of the spectrum. But you can also tune the coatings for ultraviolet light if you wish. That's what they did for the Hubble Space Telescope. The Hubble Space Telescope has a simple coating only of magnesium fluoride. And the only reason why they use that is because magnesium fluoride is the only coating out there that does not absorb ultraviolet light. It transmits it. So the aluminum is able to reflect it, take the light in, and reflect it back out without being absorbed by the magnesium fluoride. So that's why the Hubble telescope was only coated with magnesium fluoride. Other coatings would, your ultraviolet light would be definitely degraded big time by using other coatings. So you can use different coatings for doing different for specifying certain wavelengths that you want to capitalize on, such as hydrogen alpha light, whatever. You can move the spectrum. You can optimize the coating formulas so you can make it more reflective for blue light, ultraviolet light, red light, or whatever.
How long does the whole coating process take?
The coating process starts with the glass coming through the door. So it's packaged up, which takes up to several minutes to unpack it. Then the optics need to be stripped. They're placed in a solution of ferric chloride, typically, or other solutions, depending on what kind of coatings are on there, like chrome or whatever. So the coatings may take up to anywhere from a day to a week to strip, depending what type of coatings they are. Then the glass has to be chemically cleaned, and then it's placed in the chamber. And every mirror is has to have a special jig made for it and adjusted. And so the actual pump down itself, once it's in the chamber, you're looking at probably a couple of hours of doing the actual. So once the optics are put in the chamber and you start the pumps up, typically it's done in about 2 hours. And then the mirror has to come out, and then it has to be put in the oven and baked overnight, and then cooled off very slowly. So, and then it has to be, basically examined and make sure everything's okay. You don't want to have to redo the whole thing over again. So, which does happen a few times, but not very often. But yeah, there's a lot of work. So basically it's almost 4 hours to do 4 hours of attention. Basically half a day's work just to do one pump down for a single mirror.
How close do commercial telescope makers follow the meticulous approach you do? How do they differ?
They're probably doing just as well. They got better. They definitely probably have better equipment nowadays than I have right now. My machine is it's an old unit, and it doesn't use all of the fancy processes that they use now. So now they use my system is all thermal evaporated, so you're limited as to what type of materials you can evaporate with thermal methods. Some of the new coatings now use electron beam guns, so they're able to use titanium dioxide coatings, silicon dioxide coatings, that sort of thing. But those coatings are mostly meant for dielectric mirrors. So there's nothing wrong with dielectric mirrors. The only thing is, like I mentioned, if anything was to go wrong with your dielectric mirror, it's done for. You can't strip those mirrors. The only reason why is because the dielectric material is very, very close in chemistry to the actual glass. So you can't strip those dielectric materials without destroying the glass. So if anything goes wrong with those dielectric mirrors, you got to throw them away and buy new ones. So what's nice about the thermal process is that I'm using a mirror coating first, which can be stripped, and then on top of that, I put the dielectric mirrors coating, so they can be. So the whole mirror can easily be stripped if you have an enhanced mirror coating that has a base layer of aluminum on it. So the coatings are quite durable, even still, but I'm limited as to what I can do for anti-reflective coatings. So I can basically only do the magnesium fluoride coatings at this point. I can't do that. I'm not capable of doing the multi-layer coatings that you see commercially.
We have one last question. Paul wants to know if his Schmidt-Cassegrain telescope is 16 years old. Should he be worried about the coatings on the mirror and the corrector plate?
No, I've seen those mirrors last, because they're sealed. They typically last quite a long time. It's the corrector plate. That's the problem with the corrector plates. They can't be stripped. Okay, those are dielectric coatings on there. So, yeah, the problem with that is that those coatings on the corrector plate, if they were to go, unfortunately, you cannot strip those coatings. So they got to be brought back to the manufacturer and either replaced or whatever. So, but the mirror should be fine unless you see like any black spots or anything like that. Yeah, that's unfortunate with the Schmidt cast screens. If the correct, but you know, with the multi coatings, so like I said, the multi coatings of today, they should last a pretty long time. The older coatings, back in the 70s and that, I don't know when they started introducing multiple coatings on Schmidt cast screens, but the earlier coatings were just magnesium fluoride, and they would only last so long. Actually, they would only put the magnesium fluoride coating on the inside surface of the corrector only, because the outside coating would be more easily damaged by environmental attacks. So for a while they actually just coated the inside surface of the corrector. But with the multi-layer coatings out there today, they're super durable. If you keep them, if you take care of them, they should last you a lifetime.
All right, thank you so much, Alan. Lots
Thank
of
you.
useful information, and I'll bet you we can probably go for another 15 minutes with questions, but we have to move on. So thanks to our speakers, Andy, Jenna, Alan, and for Steve for making a special appearance.